Alright, so for today's video, I wanted to just go over three different types of limits that we didn't get to cover in class today. But just to recall what we did today, we were able to cover the conjugate method in class. So once again, there are different ways to evaluate limits. Direct substitution is one of them. That's definitely one of the ones you always want to try first. If that fails, you can always ask yourself if you can factor. If you can't factor, you can consider these other methods that we're about to talk about. So the conjugate method is what we covered today in class, and we'll be covering these three other ways to evaluate limits. Okay, so let's go over to the page we were working on today, which is page 11. We're going to finish example number 8, example number 9, and example number 10 in this video. So let's look at example number 8, which is called the fraction action problem. And let's go over this problem. So once again, our algebra skills are going to be very important in helping us evaluate this limit. So to start this off, if we look at this limit right here, the first thing you always want to try to do is plug in the x value, directly substitute in x equals 0 into this expression, but you'll realize that you'll get the situation where you have 0 over 0. And we call that the indeterminate form. So because we have the indeterminate form here, 0 over 0, we have to resort to a different way to evaluate this limit. So I'm going to go ahead and rewrite that limit that they gave us. Limit as x approaches 0 of 1 over x plus 3 minus 1 over 3 all over x. So here, the best tip I can give you is we want to work with the numerator first and simplify that. And that will allow us to further simplify this whole expression. So let's focus on the numerator that we have here. And if you notice, by looking at this numerator, you have different denominators. So what you want to do here is find a common denominator. So in order to do that, I'm just going to rewrite this as limit as x approaches 0 of, I'm going to add more space to this, so 1 over x plus 3 minus 1 over 3. All that is over x. And so we're going to multiply this fraction by 3 over 3. And then we're going to multiply this fraction, the 1/3, by x plus 3 over x plus 3. By doing this, this will allow us to get a common denominator in the numerator. So let's simplify that. The limit as x approaches 0 of 3 over 3 times x plus 3 minus, be real careful here, make sure you have the parentheses in the numerator, x plus 3 over 3 times x plus 3. And please remember, this is just coming from the numerator. And please recall that all this is all over x. So I'll put that all over x. Now that we have a common denominator for both of these fractions, we can combine them using the rules of subtraction here. So we'll have the limit as x approaches 0. And please be real careful here. Make sure that you distribute that negative using the distributive property. So you should have 3 minus x minus 3 all over 3 times x plus 3. And all that is all over our x. Notice here that you're able to cancel out the 3's. Okay. So now we are left with the limit as x approaches 0 of negative x over 3 times x plus 3 all over x. Okay, and now we have simplified further. So we came from two different fractions being subtracted from each other, and now we combine them, and so we got this simplification for our numerator. So we're almost there, but now this is a very important step that I need you to be able to see. So we have this fraction divided by the denominator. So another way to read this is negative x over 3 times x plus 3 divided by our x. So this right here is another way to rewrite this right here. And then if we use the rules here, we'll turn this division symbol into a multiplication, and we'll take the reciprocal of this. So this is equal to the limit as x approaches 0 of negative x over 3 times x plus 3. Change to the multiplication sign, and then take the reciprocal. So you have 1 over x. And then you'll notice that these x's will cancel. And ultimately, you are left with negative 1 all over 3 times x plus 3. Awesome. And so now we are able to substitute in this x value. So we'll plug in 0 in for x here. And you should get this. Negative 1 over 3 times 0 plus 3 equals negative 1 over 9. Once you multiply that out. So negative 1 over 9 should be the correct answer for this problem. Okay. So once again, this type of problem is called the fraction action problem. Please make sure that you get common denominators when you're dealing with these types of expressions. So that will definitely help you on the homework. Now let's go over to example number 9, which is called a problem with x plus h. In example number 9, we kind of already have worked with this in class today. Today in class, we were working with the difference quotient. And all we did today was really just work with the algebra and our new knowledge of limits. We haven't really talked about the meaning of the difference quotient, but I promise you that we will. So this right here, this whole expression is really the difference quotient, but for a specific function. So what they did here is that they plugged in and they found f of x plus h. They subtracted it from f of x, and they put it all over h. So they already did that here. So let's go ahead and solve this problem. And once again, if you plug in 0 directly into this expression, wherever you see an h, you'll notice that you will get 0 over 0. And once again, that is the indeterminate form. So we can't directly substitute in h equals 0 into this expression. So we have to simplify this expression. So let's go ahead and do that. So this right here is going to be equal to the limit as h approaches 0 of 4 times, You can use Pascal's triangle here if you want. You should get x squared plus 2xh plus h squared. Distribute the negative 3, so negative 3x minus 3h negative 3x minus 3h plus 2 minus 4x squared plus 3x. Sorry about that. Should just be plus 3x minus 2. All this is all over h. So then, there's one more thing we got to do before we move on. We're going to make sure we distribute this 4 into each term there. So I'm going to go ahead and rewrite that. So equals limit as h approaches 0 of 4x squared plus 8xh plus 4h squared minus 3x minus 3h plus 2 minus 4x squared plus 3x minus 2 all over your h. Once we simplify and get to this part, we can cancel out some terms. So the negative 4x squared and the 4x squared cancels out. The positive 3x and the negative 3x cancel out. And the negative 2 and the positive 2 cancel out. So then we can rewrite this limit as equals limit as h approaches 0 of 8xh plus 4h squared minus 3h all over h. And please notice that when you get to this expression, if you look at the numerator, we can factor out an h in the numerator. So let's go ahead and do that. So this equals the limit as h approaches 0. Factor out the h from the numerator. So you're left with 8x plus 4h minus 3 all over h. Once we factor out the h in the numerator, notice that these h's will cancel out. So that is just equal to the limit as h approaches 0 of 8x and I think there's one thing. Yeah, so 8x plus 4h minus 3. Yeah, sorry about that. So I'm just double checking my work here, just making sure. So we distributed this, so we are good for h squared. Yes, so we're good. Just double checking my work. So we're good here. And then if we simplify even further, when you get to this point right here, please make sure that you plug in h equals 0, wherever you see the h. So that is equal to 8x plus 4 times 0 minus 3. You'll see that this term will cancel out. So ultimately, you are left with 8x minus 3. And that would be your final answer. Okay, so you should have got an 8x minus 3 for example number 9. So that is the way that we simplify this expression. Once again, this is just really the difference quotient, which is what we looked at in class today. So all we did here was really just simplify the difference quotient for a specific function. So hopefully example number 9 makes sense. Now let's look at example number 10. For example number 10, we got to just be a little bit more careful. Here we're dealing with a piecewise function. In example number 10, they want you to find the limit as x approaches 2 of f of x. They give you f, which is a piecewise function. So you have two different functions at different intervals. So for this question, I think it's helpful to draw just a little picture. It doesn't have to be super accurate, but I think a picture would probably help with visualizing what's happening. And notice that we're focusing on this x value of 2. I'm going to put 1, 2. And remember, we're not going to be real accurate here, but at x equals 2, that's our focus. And if you look at this top section, here, when x is equal to 2 or greater than 2, we are on the graph of a quadratic function. So what I'm going to go ahead and do is plug in this 2 into this quadratic. So you should get 2 squared minus 1. That should equal 11. So at x equals 2, we're at a y value of 11. Once again, this is not the scale. It doesn't have to be for this problem. And you'll see why. So at x equals 2, we're at 11. Okay. And then after x equals 2, so for x values greater than 2, for any x value greater than 2, we're on this quadratic function. So notice that this quadratic function would be opening upward. So it kind of look like this. Once again, not accurate, but all we got to know is that it's going upwards from there. And then now, when x is less than 2, we're on a linear function. So one little thing I want to point out here is there is actually a hole present right here. There's some type of hole present. Notice that when we looked at this top one, we plugged in x equals 2 into this function because it's defined on this function. But here it's not defined on this linear function. So what we could do to figure out where the hole is plug in this 2 into our linear function. So let's go ahead and do that. So we have 5 times 2 plus 2, which should equal 12. So let me extend the graph. So at a y value of 12, when x is 2, we have a hole at 12. So when x is less than 2, we're on this line. So we don't have to be real accurate, but the y-intercept of this line is positive 2. So on the y-axis, I'll just put positive 2 right here. And once again, it doesn't have to be super accurate, but I would just draw a line from the hole crossing that. So it'll look something like this. And then remember, this is just a sketch. And this is going to give us a better idea on how to approach this problem when we're finding the limit. So now let's go ahead and find the limit as x approaches 2 of f of x. Please remember that when you're finding limits of these numbers, you have to test both the right-hand limit and the left-hand limit. Okay, so let's go ahead and do that. Let's go ahead and find the right-hand limit. The limit as x approaches 2 on the right-hand side of this function. So if we look at our sketch here, when we're coming from the right-hand side, what y value are we approaching? Notice that when we're coming from the right-hand side towards 2, we're on this quadratic function. So as x approaches 2 from the right-hand side, we'll go ahead and plug in this 2 into our quadratic function, and then once again, that'll just be equal to 11. Okay. And I'll just show that work here. That'll be equal to 11. Okay. And if you want to be real specific here for f, you could have plugged that in. We could have said this as well. So I want to be real clear. This is an alternative way to write this. If you want to be real specific, we can say the limit as x approaches 2 for the right-hand side deals with 3x squared minus 1. And that'll be equal to 11. So once again, these represent the same thing. And then now, let's test the left-hand limit. So the limit as x approaches 2 from the left-hand side. If we look at our graph, as we're approaching 2 from the left-hand side, we're on this linear curve. And what y value are we approaching? You'll notice that we're approaching the y value of 12. So, from the left-hand side of this function, of this piecewise function, we're approaching 12. And if you wanted to, you can also say the limit as x approaches 2 from the left is dealing with this function, 5x plus 2, which is equal to 12. Okay. So now that we tested both the right-hand side, the right-hand limit, and the left-hand limit, what can we say about the overall limit as x approaches 2? So therefore, the limit as x approaches 2 of this piecewise function does not exist because the limit as x approaches 2 from the right-hand side of f of x does not equal the limit as x approaches 2 from the left-hand side of f of x. Okay, so that would be your final answer for this question. So hopefully that makes sense. And that is example number 10. So you'll definitely see a good amount of piecewise functions in this class. And we'll definitely investigate them in our next topic, which is called continuity. So you'll definitely go ahead and see that on there. And I just wanted to go ahead and go over just one more idea from the homework, just to help you all out. So on the homework, if you look at the homework, at the very last page where it's telling you to find a limit, questions 83 through 89. If you look at those questions in the homework, they tell you to find the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. So this right here is an alternative way to write the difference quotient, which is what we talked about in class. Okay. So, and remember in class, we looked at the difference quotient as limit as h approaches 0 of f of x plus h minus f of x all over h. So here, instead of using h as that variable, what they're using here is delta x, which will represent the same thing once we explain what the difference quotient means in the context of calculus. So delta x and this h are interchangeable, and that's an important point I want to make. So if we look at question 85 on the homework, let's go ahead and try that out. So you have f of x equals x squared minus 4x. So today in class, we looked at this difference quotient, but let's go ahead and apply this new alternative representation of the difference quotient. So for question 85, we're definitely going to have to find f of x plus delta x. And please remember, when they want you to find x plus delta x here, sorry, f of x plus delta x, wherever you see an x, you're going to plug in x plus delta x. So same idea with x plus h. So let's go ahead and do that. So you have x plus delta x squared minus 4 times x plus delta x. Okay, so now that we have x plus delta x, let's go ahead and simplify that first before we fully use the difference quotient. So you should get x squared plus 2x delta x plus delta x squared. So please remember, you can treat delta x as just a variable. So that's why we put it like that. And then distribute the negative 4, so minus 4x minus 4 delta x. Okay, so now that we simplified f of x plus delta x, let's go ahead and evaluate this right here. So therefore, the limit as delta x approaches 0 is equal to, I'm going to just copy this over here, equal to that, which is once again representing f of x plus delta x minus f of x. Our f of x is x squared minus 4x. So let's plug that in. All over delta x. All right. So now at this point, we see if there are any terms that we can cancel out, and you'll see that there is. So you'll see that this right here will evaluate to minus x squared plus 4x. So let me write that down there. Minus x squared plus 4x. And you'll see that the 4x's will cancel out, and the x squares will cancel out. So if we simplify further, we have the limit as delta x approaches 0 of 2x delta x plus delta x squared minus 4 delta x all over delta x. And remember, you can think of these delta x's as h's. So if you look at the numerator, we can factor out a delta x. So that would look like this. Limit as delta x approaches 0 of factor out the delta x, one of them, and you have 2x plus delta x minus 4 all over delta x. And then similarly, you will notice that these delta x's will cancel out. And that'll be equal to the limit as delta x approaches 0 of 2x plus delta x minus 4. And then at this point, now we're actually able to plug in our delta x value of 0. So we'll plug in our 0 into delta x. So we have 2x plus 0 minus 4, which evaluates to 2x minus 4. And there you go. That is the correct answer for question 85. One important thing to make sure is that you keep the limit notation throughout the whole way, and you're consistent with the algebraic steps along the way. So be real careful with that, because one small algebraic step can definitely affect your answer. Okay, so just be real careful with the algebraic steps that we did in this problem. Okay, so after going through these examples today, I just want to go ahead and go back to our homework and talk about the ones that you should be able to complete. So at this point, based on the problems that we looked at, and based on the new knowledge that we talked about using Pascal's triangle today, so on the homework for the finding limits, you should be able to complete questions let's see, 53 through 62, all the odd problems on those. And let's see, so I don't know why I said 62, it should be 61, right, because you're just doing the odd. So you should be able to complete questions 53 through 61 based on what we just did. And questions 63 to 74, we'll go ahead and talk more about that next class, okay? So I rethought about it. I think it's best that we go over that material on Thursday. So we'll go over the squeeze theorem on Thursday, and we'll talk about how to approach those limits in questions 63 through 73. So we'll talk about those on Thursday. But for right now, if you look at the last page, questions 83 through 89, you should be able to complete those based on what we talked about. So please make sure that you complete these questions on the finding limits homework. And also don't forget to complete the difference quotient. Problems that I gave you. And I believe there are just 2 questions on there. And they use Pascal's triangle. Okay. So hopefully these examples made sense. Once again, if you have any questions, please feel free to reach out to me at any point. I'm always here to help you out. I hope you have a great rest of your day. Bye-bye.